Hardy-Weinberg Equilibrium. What does it mean? When a population is in Hardy-Weinberg equilibrium, it is not evolving. This means that the allele frequencies remain the same from generation to generation. In reality, these populations do not exist, but it is important to understand the idea of evolution.
For a population to be in Hardy-Weinberg equilibrium, a number of conditions have to be met. So the first condition is there can be no mutation in this population, because that would interrupt the steady frequency of alleles. Second, there has to be no natural selection, so certain traits can't be more useful than others. Third, there has to be a infinitely large or at least very large population, so it can't be small because that makes genetic drift easy. So large population. Next, you have to have random mating, so no sexual selection or anything like that. And the fifth one is going to be no migration, so no organisms going in or out of the population. And then there's another two. These are the basic five, but then there's another two that are kind of like sometimes included, and that is each organism produces the same number of offspring, and that also that all members breed.
Okay. In order to solve Hardy-Weinberg problems, you need to use these two equations. The first equation is P plus Q equals 1. And the second equation is P squared plus 2PQ plus Q squared equals 1.
Okay, so each of these variables, these P's and Q's, they each correspond with something in the population. So the P over here is the frequency of the dominant allele. And then the Q is the frequency of the recessive. So these two have to add up to 1.
For the second equation, P squared stands for the frequency of individuals with a homozygous dominant genotype. That means if our allele is represented by A, it will have two capital A's. 2PQ represents the number of individuals with the heterozygous genotype, meaning their genotype will be represented by capital A, lowercase a. And Q squared represents the frequency of individuals with the homozygous recessive genotype, represented by little a, little a.
So what's important to remember is that P and Q stand for individual alleles, so that corresponds with only A, big A, and only little a. But the P squared, 2PQ, and Q squared all correspond with full genotypes. So this is kind of a single allele situation, but these are double allele situations. Okay, so now let's work through some sample problems. So for our first sample problem, you have a population in which you know the percentage of the homozygous recessive genotype, which is 36%. So using that, we're going to calculate the following.
Alright, so for part A, we're going to calculate the frequency of the little a genotype. For part B, the frequency of the little a allele. For part C, the frequency of the capital A allele. For part D, we're going to calculate the frequencies of the big A, and the big A, little a genotypes. And for part E, the frequencies of the two possible phenotypes if capital A is completely dominant over little a.
So you can see that with just one number, we can solve for all of this stuff.
So in this first problem, problem number 1, we're given the homozygous recessive genotype as 36%. 36%. So that is A is 36%. Okay, so given the homozygous recessive genotype, we can find Q squared, which is equal to 0.36. Okay, so for the next part, we're going to find the frequency of the little a allele. So since q squared equals 0.36, taking the square root will give us q, which in this case is equal to 0.6. Okay, so for part C of this problem, we're going to find the frequency of the capital A allele, which is equal to p. So we're going to use the equation p plus q equals 1. So plugging in q as 0.6, get p plus 0.6 equals 1, so p equals 0.4.
So here we're trying to find the frequencies of the genotypes for the homozygous dominant and the heterozygous. So we know that p squared equals the homozygous dominant, which is AA. And we already found P before, so P, which is going to be 0.4 squared, equals 0.16. So that is our AA frequency genotype. Then we've got 2PQ is going to equal our heterozygous. So that means that we know our P and Q values, so we just plug those in. 2 times 0.4 times 0.6, and that's going to equal 0.48. So there we've got our frequencies for the two genotypes. Okay, so now finally we're going to try to find the phenotypes. So if the big A is completely dominant over the little a, that means that that phenotype is going to occur with these two genotypes. So we've got our frequencies for those here. So that's going to be 0.16 plus 0.48 equals 0.64 is going to be our dominant phenotype. And then we know that everything else, and we also know what q squared is earlier, is going to be 0.36. So that is our recessive. This is the little a, 0.36, and that's our recessive. So those are your two phenotypes.
Okay, so sample problem number 2. Within a population of butterflies, the color brown is dominant over the color white. 40% of all butterflies are white. Calculate the following.
So for part A, we're going to find the percentage of butterflies that are heterozygous. And for part B, we're going to find the frequency of homozygous dominant individuals. So that's going to have this genotype.
So for this next question, we're given a population of butterflies where brown is dominant, meaning it's big B, and white is recessive, so it's little b. So in this population, 40% of the butterflies are white, meaning they have the genotype little b, little b.
So as soon as you see this BB, you can think of that as q squared. So that means you've got 40% equaling q squared, which is, this can be rewritten really as 0.40 because percentage is just a type of frequency. So then for part A, we're trying to find the percentage that are heterozygous. So that means we're going to need to find both the Q and the P values. So this is just a square root kind of thing. Q is going to equal, we're going to round it out to 0.63. And then since we know P plus Q equals 1, that means that P is going to equal 0.37. So then in part A here, we're trying to find that heterozygous frequency. So we're going to do 2 times P times Q. And that equals 2 times 0.63 times 0.37. And that's going to equal just about 0.47. So that is your heterozygous frequency.
So next, what we're going to do is we're going to find the homozygous dominant. So I'm just going to move this out of the way. Alright. So to find the homozygous dominant, you're going to want to take your p-value, which you know to equal 0.37. So since the frequency is represented by p squared, we can just square these values here, giving us 0.14. So that's going to be the answer to the frequency of your homozygous dominant individuals.
For our third sample problem, we're going to be dealing with cystic fibrosis. And this is a genetic disorder, and it leads to congestion in the lungs and infection, and your body can't really absorb nutrients. So it is a recessive condition, and it affects about 1 in 2,500 children in the Caucasian population in the U.S.
Okay, so given that, we're going to calculate the following. For part A, we're going to get the frequency of the recessive allele, represented by little f. For part B, the frequency of the dominant allele, big F. And then for part C, the percentage of heterozygous individuals. So that's individuals who have big F, little f, represented by 2pq in our Hardy-Weinberg equations. Okay, so for part A, that's the part where we're getting the frequency of the recessive allele. So we're going to start off, we're given that 1 over 2,500 people are affected by this disease. So since this is this is going to be our recessive genotype, so that's going to give us q squared, and that's going to equal 0.0004. And then next we're going to take that, and since we're finding the allele that's represented by q, so we're going to have to take the square root of 0.0004, and that's going to give us 0.02.
Then for part B, we're trying to find the dominant allele, so in this case big F, and using the equation P plus Q equals 1. It's pretty simple because we already know what Q is, so we can substitute that in. P plus 0.02 equals 1, and we find that our P value is going to equal 0.98.
Okay, so now for part C, we're going to find the percentage of heterozygous individuals in the population. So that's going to be the individuals with big F, little f. And in our Hardy-Weinberg equations, that's the one that is 2pq. So since 2pq equals the heterozygous individuals, we can just plug in our p and q values from parts A and B. So we'll get 2 times 0.98 times 0.02. So we do the multiplication there, and that's going to give us 0.0392, which is about 3.9%.
So you can see here the real-world application of Hardy-Weinberg, because we started off with just the q squared, or how many percentage of people that were affected by this and who had the disease, and then using that we were able to go to a heterozygous, and so that ended up giving us the carriers of the disease. So we can find the people who have the ability to pass the disease on to their children without actually having it themselves. And this is really useful for doctors around the world. Okay, so really what to get out of this Hardy-Weinberg, what do you really need to know? So make sure you know the conditions that are necessary. So we had those 5 to 7 conditions that a population needs to be under in order to be in Hardy-Weinberg.
All right, then next you're going to want to make sure you know the equations. So those were the two equations that we went over. So that's P plus Q equals 1, and then P squared plus 2PQ plus Q squared equals 1. And then finally you also want to know how to solve. So those were the sample problems we did, and just remember, you can find the different allele frequencies and the genotypes given just one piece of information.
So that's that.